Unsiloed podcast is produced by University FM, elevating the stories of your institution.
Welcome to Unsiloed. This is Greg LeBlanc, and I'm here today with Martin Nowak, who is a professor of mathematics and biology, or biological mathematics, mathematic biology, right? Combining both of them, and also at Harvard University. Did I say that? And also the author of a bunch of books. This is sort of the classic, the magnum opus, Evolutionary Dynamics, exploring the equations of life. And I remember when that came out, gosh, back in 2004 or so, I think it was. And then 2006. Yeah. And then this is sort of a more accessible version of a lot of the same material. It's called SuperCooperators, Altruism, Evolution, and Why We Need Each Other to Succeed. And the most recent book is called Beyond, which is a bit of a departure, and hopefully talk about that. Welcome, Martin.
Hello. Welcome, Greg.
So I think that there's a lot of rich points in all of your work, but I think probably the most profound point that you're making is that Darwin is incomplete. Darwin talks about variety and selection, and you highlight that there's a third mechanism which is important and necessary for evolution to do its work, and that is cooperation. And we can't really talk about the great transformations, the stuff that John Maynard Smith talked about, without really digging into cooperation. And I teach a course on game theory, and so of course, economists also talk about cooperation. And usually at courses like mine, we kind of stop after we have articulated just a couple of the mechanisms of cooperation. And you highlight there are these 5 mechanisms that we need to discuss. And hopefully we'll dig into all of them. But I guess where I thought I'd start out is biology is really pushing the envelope in this area in ways that I think economics at one point thought that they would push. I think economists thought that this was a domain that was kind of they owned this domain. They were going to be the ones that were going to be advancing it. But biology has done so much, mathematical biology has done so much to articulate how cooperation works. Was that surprising to you? I mean, when you encountered economics?
I would say, the contribution of economics is tremendously important, and you are completely right in stating that game theory started as an economic theory. John von Neumann and Oskar Morgenstern. John von Neumann, a mathematical genius, and Oskar Morgenstern, an Austrian economist, actually collaborating in Princeton, developed this field of mathematics game theory in order to understand strategic decisions of humans. So it started definitely in that area. And only with the work of John Maynard Smith, I would say in the 70s, was it then suddenly applied to biology. So he then discovered this rich way to analyze strategies and behavior, and said, let's apply this to animals. And then came the important work of my PhD advisor, Carl Sigmund and Josef Hofbauer, in that book, where they discussed the replicator equation. I think for me, that's really the foundation of evolutionary game theory. The equation was first described in a paper by Peter Taylor, actually, Taylor and Jonker. But Hofbauer and Sigmund then wrote the book and so really analyzed this equation. So it moved from economics to biology. And on that way, one important thing happened. And this is the idea of Nash equilibrium and rationality was retained, but moved kind of in second position. And first position was now this idea of a population and evolution. That is evolutionary dynamics. So it is no longer just a rational solution concept. It is more like let natural selection choose a strategy.
Mm-hmm. Now, but you started off in mathematics. How did you get interested in mathematical biology? You tell a story in the book. This book, SuperCooperators, it's kind of, there's a bit of a memoir element to it as you walk through the development of your thought.
SuperCooperators was written together with Roger Highfield, and he's a fantastic writer, and he interviewed me, and then together we kind of came up with those things. So he asked me a lot about my life. I started as a student of biochemistry. So when I started my university degree, I was fascinated by science and I wanted to understand the chemistry of life. But I had no clue about the purpose of mathematics. And in my first physics class, I was blown away when the professor said, let us now calculate something in order to understand what is going on here in this experiment. So I was amazed that mathematics is actually there as the language of natural sciences. So I moved as quickly as I could through my chemistry degree towards theoretical chemistry, but I finished my undergraduate degree in chemistry, and only then I started my PhD thesis with Carl Sigmund in mathematics.
Mm. And of course, the biologists have been mystified in part with cooperation. I mean, I think in the early days, the biologists, I think they had to think in terms of kin selection. I mean, kin selection and tit for tat were about as far as they were willing to go. Maybe you could talk a bit about the early days when the notion of reciprocal altruism and kin selection were developed. How did those
Yes,
first enter the conversation?
yes. So this would be two of the 5 mechanisms that I'm describing in the 2006 science paper. And so I would say that even in Darwin's writings, you find aspects of cooperation where he says that if you imagine 2 tribes and in one tribe there's always the individuals always help one another and in another one they don't, and so then this first one might be winning over the other one. It's sort of, this is a verbal statement, but it's maybe he doesn't really understand the tension between individual selection and selection on a higher level.
Yeah.
But you are right. So there would then be this discussion that, for example, that animals don't really kill each other because that would be very bad for the species. That's a group selectionist argument. And the group selectionist argument is not necessarily always wrong, but you have to be careful and wonder when it really applies. So then I would say came important work by Bill Hamilton, and I knew Bill Hamilton in Oxford actually, and I admired him very much. In his PhD thesis, he gave a theory for how natural selection would actually favor cooperation among close genetic relatives. So if you are my brother, or if I'm thinking of helping my son or something like this, so if there's a very close genetic relationship, then I could pay a cost for the other person to have a benefit. And that could work out because the gene that asks me to do that is also present in the recipient. So this also goes back to Haldane's famous remark, I will jump into the river to save 2 brothers or 8 cousins. So there was this idea of how to get cooperation among close genetic relatives. Of course, it's not a theory for how to get cooperation among unrelated individuals. And also, approximately until 2004, I would have thought this is really one of the most successful theories in mathematical biology before I really began to investigate it. And then, of course, came the discovery of the flaws in that theory, and that led to the famous 2010 Nature paper with Ed Wilson, where we actually critique that theory, but decisively also prove that inclusive fitness is a quantity that you simply do not encounter in natural situations. And later in a paper, we also showed that Hamilton's rule in the modern formulation, not actually in the original formulation. In the original formulation, Hamilton's rule is almost always wrong, but this was already known actually for a long time. People kind of ignored it because this was pointed out by Carlin in a Fisher lecture. Robert May was present in that Fisher lecture. You can make easy calculations where you show that classical Hamilton's rule, when you say that benefit times relatedness is greater than cost, and you really mean benefit and relatedness and cost, that it doesn't work like that. But there is the so-called extended version of Hamilton's rule, and that was then considered to rescue the theory. And there was a 2017 paper in PNAS where we actually showed that this is just a statistical identity that is not a biological statement. So in the extended version, Hamilton's rule is meaningless. And inclusive fitness is a quantity that is typically not present in normal situations. So it is built on such fragile assumptions that you never encounter them in the world. But the good news is also in the 2010 paper, we show it's absolutely never needed. So you can calculate everything you like about evolution of eusociality, workers raising the offspring of the queen, or workers policing, or anything, without ever using or needing the concept of inclusive fitness. And that, I think, is a great advantage. So this is the first mechanism, which I call kin selection. The mechanism still makes sense to me, but the dominant mathematical exploration of it is very problematic. And this was pointed out in the 2010 paper.
Well, look, I mean, as long as people have been talking about people, right, and talking about society, I mean, we've known that people are very cooperative, right? I mean, we see societies, we see altruism, we see charitable behavior, we see religions, and so the folks who in social science and the humanities, I mean, we take these things to be facts. But how did biologists think about it before these more complex understandings of cooperation? I mean, certainly, I
I
mean,
mean, as I said, the earliest explanation was that cooperation within the members of a species is good because it is good for the species. I think this would be very early ideas. Then somehow came the kin selection idea with close genetic relatives. Then I would say came game theory, and the game theory then used what is called direct reciprocity. So then the second mechanism is direct reciprocity, and this is that our interactions are usually not just one shot, they are repeated. So we are talking today, but we may also talk tomorrow, or I meet the same person in the office again and again. So if we put this so-called prisoner's dilemma in the context of repetition, then cooperation is actually possible. And there was a famous paper by Robert Rivers, and then the book by Robert Axelrod, Evolution of Cooperation. So Axelrod conducted these tournaments, computer tournaments in the late 70s, and the winning strategy in those was tit for tat. And tit for tat was then described in his book as the world champion. So this is how you play the game of cooperation if it's repeated. This is where my PhD thesis started with Carl Sigmund, because we were aware, of course, that tit for tat has an Achilles heel. So there's something problematic about tit for tat. And this really is that it is unforgiving. So if two players play tit for tat and one starts to defect, then the other one defects immediately. And then the first one hits back and the second one hits back. So it is kind of an endless vendetta. And therefore, in a world with errors, tit for tat does not perform well.
mm-hmm.
So that in my PhD thesis, we asked then the question, how do we improve over tit for tat in a world where errors are possible or likely? And also, let us not design artificial programs that play tournaments. Let us ask natural selection to design strategies for us. Mm-hmm. And then came the observation of generous tit for tat. And that is a big improvement over tit for tat, because now I cooperate always when you cooperate. But sometimes I cooperate even if you defect. So generous tit for tat is now the evolution of forgiveness. It's very important in this context to be able to forgive. If somebody harms you, you have to forgive it after some time and start cooperating again. Otherwise, everything gets destroyed. So the first winning strategy that we had here was generous tit for tat, and generous tit for tat is still, in my opinion, one of the strongest strategies to play the repeated prisoner's dilemma. Later in my postdoc, we discovered another strategy that we call win-stay-lose shift. And win-stay-lose shift is actually also a very simple principle. So I keep doing what I'm doing if I'm doing well, and I try to do something else if I'm losing. And that leads to a strategy that always cooperates with itself, that can correct mistakes, and that also is actually stable with respect to neutral drift invasion by unconditional cooperation.
Right
so
now,
these two strategies are remarkable strategies, but the field has also many new things to say in direct reciprocity.
Now, when you're trying
So the
to,
indirect. Sorry, please.
I was saying, a lot of this work involves simulations, right? How much of the development of this field of evolutionary dynamics required the use of simulations, and how much of it could be done entirely using closed form solutions and mathematical.
This is a very good question. So in evolutionary dynamics, most differential equations are actually nonlinear, and for those nonlinear equations, you are hard pressed to find analytic solutions with paper and pencil. And therefore, in order to see what is going on, you really want to look at a computer simulation. Also, then later, I introduced, for example, stochastic evolutionary game theory, a probabilistic description where you are studying random processes, and you want to see this with computer simulations. But it usually works like this: that the computer simulations, they give us a first idea of what's going on. So for me, this is like looking under the microscope, and now we see what's going on under the microscope, and now we want to prove something. So in many of my papers, I really try to actually prove something in the end, because a computer simulation is always at best an example. It's a particular case. But if you want to formulate a law of nature, you have to have a proof. So even if you can't solve the equation analytically, you could still prove conditions, for example, for evolutionary stability, or can calculate fixation probabilities and this sort of thing.
Now, look, we need to understand cooperation just to understand how organisms evolve, right? We need to understand how animal societies evolve. But there are certain things that are particular to humans, right? I mean, humans seem to be able to achieve levels of cooperation that the other animal species can only dream of.
Yes, brilliant. Yes, spot on, right. I think this remark brings us exactly to the next mechanism, which I call indirect reciprocity. The idea here is now that yes, interactions are repeated, but not necessarily between the same two people. So I might help somebody who is a complete stranger, or in my class, I often talk about the New York subway hero, this brave man who saved another person who fell in front of the train. And sort of this is not really the beginning of a long repeated game. And so the question is, why do we have this instinct that we want to help, even if it is with somebody we don't know and where presumably a direct interaction is unlikely? And here the proposal is that this works because of reputation. So you help somebody and that gets you the reputation of a valuable member, and that is a person who receives help. Or you refuse help to somebody, and that then will earn you also refusals in the future. And very soon there were experiments done by Manfred Milinski and Klaus Wedekind, published in Science, where they have students sitting in front of computer screens, and the students are asked, do you want to give $1 for somebody else to receive $3? And then they do this, and then those people who do this also very often receive $3. And this is how indirect reciprocity works. And this became a big field.
Go ahead.
Yeah, it became a big field, and there are many, many papers, and it's a fascinating area.
Now, it's really weird, though, right? I mean, I can understand why if it were about trust. So somebody wants to develop a reputation for being trustworthy because other people will interact with them. But how does developing a reputation for being altruistic help an individual in terms of their fitness? This part is a bit strange, right?
No, I think it's a good question. It's very nice how you pose it. So I would say that generally trust and altruism, they almost go together, so you trust somebody. If you see that somebody is actually altruistic and not selfish, not self-obsessed, then you might trust that person. And so it goes hand in hand, in my opinion.
Yeah, I mean, we have this thing here in Silicon Valley called pay it forward. And everyone I know knows exactly what it is. And most people I know actually practice it. But when you try to describe it to somebody as an outsider, it kind of doesn't make any sense. I help people, I mentor them, I advise them, and I don't expect anything in return. But I'm oftentimes getting help and advice from other people who don't expect anything in return from me. And it seems almost like an act of faith. It seems almost sort of a quasi-religious disposition, right? Where you just have some trust that the ecosystem will get back to you what you give into it.
Yes.
Is it fundamentally irrational in a way?
No, so the way how you described it is actually indirect reciprocity. So you are a nice person, you help your students, and you think that somebody will help you. That's precisely indirect reciprocity.
Yeah.
So what we call pay it forward in that game theoretic setting is upstream reciprocity, and that works like this. So you help somebody, that person now feels completely amazing and starts to help somebody else randomly.
Hmm.
That is the typical pay it forward. So uh, the 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 example is something nice is being done to you. You have a great day. You do something nice to somebody else, and
Hmm.
that is not the same as this normal indirect reciprocity. And that is not a mechanism for cooperation. That requires a mechanism for cooperation. So indirect reciprocity can explain why people would have that, because by doing that, they are also thanked themselves. So if I help somebody, I will receive help. But if I receive help, then I will thank somebody. If that's the only story, that is not a mechanism, because there would be those people who don't do this, and they would be favored by natural selection. And so you always have to explain why natural selection favors cooperators. That's always the challenge here with these 5 mechanisms.
Yeah, I had a friend who I helped out recently financially, and then he said, "Hey, what can I do to express my thanks?" And I said, "Hey, I had somebody else help me financially before, and so I just want you to go and help somebody else, right? There'll probably be some person who's younger than you who will probably need some help in the future." And he immediately grasped what I was saying, and he said, "Okay, that makes sense. I'll be sure to do that." And in a way, what you're doing is you're kind of building up a community, and people can identify whether you're sort of part of that community or not to some degree, right? I mean,
Yes.
is there a way of signaling that you subscribe to this philosophy? I mean, is this an example? I mean, is the spatial game tied in with this? Do
Yes,
those
completely
mechanisms
correct.
work together?
Yeah, yes, yes, yes. I think this brings us to the 4th mechanism, and this is network reciprocity or spatial selection. So we are embedded in this social network, and in this social network, you interact with people, and they interact with people. And the idea here is that cooperators can form cliques, they can form
Uh-huh.
clusters, they can form communities, and those cooperators they help each other, and therefore they survive in a world where there are many defectors floating around. And if you are a cooperator, then your friends learn from your behavior and they will become cooperators. But also they benefit from your cooperation, you benefit from their cooperation. And this is precisely this spatial reciprocity, the 4th mechanism. And I described this first actually in a paper with Robert May that was published in the 1990s. That was the spatial games. Actually, then later it became evolutionary graph theory. So we moved away from spatial lattices to any kind of graph. And that is also a big field of investigation now, evolutionary graph theory.
Well, now spatial games don't require the kind of high level cognition that humans have, right? You can have spatial cooperation with presumably bacteria, right? I guess a biofilm is an example of a spatial game. Is that right? I
Very
mean,
good. Yes, very good. Yes, the spatial games don't require the high cognitive machinery that is required for direct reciprocity and for indirect reciprocity. So, for direct reciprocity, the very least is David Haig put it very nicely. He said, for direct reciprocity, you need a face. For indirect reciprocity, you need a name. So for direct reciprocity, I have to recognize that other person and kind of remember what happened last
yeah,
time when we interacted. But for indirect reciprocity, it's even more complicated than this, because I have to be able to talk to you about somebody else and what
right.
that person has done to me, good or bad. And that requires language. So for me, indirect reciprocity was exactly the selection pressure for human language in human evolution.
Right. So if you're a primate, I'll groom you if you groom me, and as long as I remember, oh yeah, this is the guy that groomed me, right? I
Mhm.
recognize his face, but in humans, you got to check their LinkedIn profile, right? Or you know, you got to consult with your friends. Hey, what about this guy? Is this guy any good? And that's really what gossip is all about, um, and what language is
Gossip,
all.
of
So you
course, is
think,
a very dangerous weapon. So on one
Yeah.
hand, gossip is needed for indirect reciprocity. On the other hand, it's also abused. So with gossip, you spread false reputation, you spread lies about somebody, and that hurts a lot. And so this is a problem. That doesn't mean that indirect reciprocity doesn't work. It just means that to achieve it is not easy.
Hmm.
Because above the interaction level, where we help one another, is this other game going on. And in this other game, the question is, do people spread lies or are they giving honest information about others? And this is another way of cooperation and defection. And you wish to think, that ultimately truth will prevail, but it will take a long time.
Yeah, I like you. I had never thought of this. I've taught strategy for a long time, and I'd never really articulated this. But you said that strategy requires sort of an action rule and an assessment rule, right? So you have to be able to understand maybe the meaning of the action or the extent to which the action was intended. It's almost like we mens rea in criminal law. We need to kind of dig in. It's not, you can't just have a pure behavioralist model for strategy.
Yes, so in indirect reciprocity, unfortunately, we formulate it usually based on action.
Mm-hmm.
And so far, I have not seen a successful approach that really takes into account motive.
Mm-hmm.
So ultimately, what we want is a game theory that is actually driven by the motive. What's the motive behind the action? Because people are very, very interested in the motive behind the action. But how to do that in game theory actually has been unclear to me in the framework of indirect reciprocity. So indirect reciprocity is I observe you, and maybe you refuse help to somebody, and I might ask the question, did that other person deserve help, or did the other person not deserve help? So I could have a complicated social norm in order to do this, but it is still based on the action.
Yeah, but of course we do this in
It is
criminal
not
law, right? So
necessarily.
we have first degree murder, second degree murder, misdemeanors, that sort of thing. If somebody steps on your foot, right? You might immediately get angry, but then they say, "Oh, I'm sorry, I didn't mean it," and then your anger dissipates. So, I mean, in everyday life and in our legal systems and in most cooperative games, we are trying to figure out whether or not this was a mistake, right? Or did somebody, we talk about trembling hand. Did the person just and that requires an even more sophisticated level of cognition, right?
Yes, absolutely right. And the trembling hand, fuzzy mind, they occur in direct reciprocity in repeated games. And in the one case, you want to cooperate with me, but you there's a slip of hand and you might defect.
Yeah, we talk about strategic bankruptcy versus, right, exogenous bankruptcy, right? If somebody's defaulting on their debts and they've absconded with all of the assets, we don't let them get out of their debts. But if they have a health crisis or something like that, then we let them get out of their debts because we want to treat them differentially based on their motives.
Yes, that's right. So in trembling hand, there is sort of a wrong move, but both you and I have the same version of the history of the game. But in fuzzy mind, the problem arises that I think you cooperated, but you think you defected, or the other way around. So we disagree on what actually happened in the past, and that makes it very complicated.
Well, you talk also about punishers, right? So I've seen these models where, in order to have a robust system of cooperation, a lot of the models suggest that you have to have people who have a taste for punishment, right? Altruistic punishment, where they are sort of the norm enforcers who are doing this. I mean, certainly you see this in Berkeley, where people will, go, you need to fix your lawn. You need to stop, using those plastic bags. Right? And you're like, what are you getting out of this? Right? You're creating conflict. You're going out of your way to be a scold. To what extent is punishment necessary to keep cooperation going?
No, I mean, there are papers on punishment, and many people think that punishment has a role to promote cooperation, but I'm skeptical of those papers because usually the studies are conducted in a way that you get, if it's experimental study, for example, that you receive punishment, but you don't know from whom, and you do not have the possibility to retaliate against that person. So what you describe is sort of the talking to a neighbor about something. I still would say it is better done friendly, that you talk to your neighbor in a friendly way so that there's no punishment aspect really there. But you could say something like, hey, your lawn looks so bad, may I come over to help you clean it, or something like this. So because punishment, if you really think about it, is a terrible idea, because in most cases, punishment is not done for any noble reason. In most cases, punishment is just an act of violence. And every well-ordered society absolutely wants to make sure that people don't take the law into their own hands, that they just don't punish others. This is for me the principle of a functioning society, that we do not punish each other. So for me, cooperation often means to refrain from punishment. And punishment is a very dangerous weapon. And I think many people have actually understood that critique, that punishment between individuals is a bad idea. And then they are still out there to say that it could be more useful if punishment is done by institutions. But also here, I'm very cautious because institutions are also not necessarily the good players all the time. They are the powerful players, and they could also use it inappropriately. So I think that punishment is extremely problematic.
Well, you talked about some of these experiments that were done across different cultures, and different cultures had different views of punishment. I was wondering if you could talk about that and what accounts for those different cultural norms around punishment.
I mean, there was this funny experiment where but it was long ago, so, in Russia, the people preemptively punished those they punished those who would cooperate, actually. So the one thing that was found is that if you cooperate, you get punished because you make us look stupid. Because the smart people know that the public cooperation doesn't work. If you cooperate in a public good game, you're stupid, you deserve punishment. And the other idea is that they preemptively punished other people. It depends on the framing. So in experimental situations, it depends on the framing. But when we conducted experiments, we actually found that if you are in a situation where people know who punishes whom, then winners do not punish. So the overall winners of the game, that was a paper published in Nature, with that title actually, winners don't punish, because those who have the highest payoff in the end have not used punishment, and they don't get punished, and they don't have fights with others. And so that's definitely highly recommended, in my opinion.
Now, you also say that the second big bang of evolution was language, right? And this is all about how humans have really turbocharged evolution and cooperation. And you did a lot of work on the evolution of language, and it seems like there are similar principles at work in the evolution of language and organisms. And I was wondering if you could talk about that, and particularly talk about this linguistic error theory that you introduced, which I found fascinating.
So I used evolutionary game theory to make some progress actually on the evolution of language, and we used evolutionary game theory for our first models, where language is a kind of game where we get a payoff if we can understand each other, and understanding each other means that I use a certain signal that means something, and it also means the same thing for you. So this was our first model for the evolution of language. And later, then we talked about evolution of syntactic communication. And so we wanted to understand what's the difference between animal communication and human language. And animal communication is really based on a limited repertoire. And human language is unbounded. It's discrete infinity. It's making infinite use of finite media. So why did we get there? And there was basically this error threshold that we identified, where if you just make sounds or so, then if you add more and more sounds, then there's always a possibility to mix them up, and then you have misunderstanding, and then you want to warn in front of if an eagle is coming, but you mistake it for the word for leopard or so, and then in animal communication you get stuck with just having a small number of signals for the most important, most dangerous situations or predators. But in human language you overcome this with this duality of patterning. So you make then certain phonemes, and these phonemes can be strung together into words, and so you discretize it, and with this discretization you overcome this error threshold, and thereby we can build a very, very large number of words out of a small number of phonemes. And the second step is that we then use syntax, we use grammar in order to build sentences out of words. And that led us then to a study of the evolution of universal grammar, Chomsky's idea. And we also gave an argument that universal grammar is a mathematical necessity. If you think of it as a search space that is employed by the human child learner of possible grammars.
But you also said that syntax really only makes sense in a world where cooperation is needed.
Yeah.
I mean, so why is that?
I mean, the very idea that I'm talking to you and we both get something out of it has something to do because we're already cooperating. So you and I cooperate, and therefore we want to understand each other. If you and I have just absolutely no cooperation going, then why would we want to understand each other? And so,
Right.
in my opinion, it was not really cooperative hunting, also because animals do that also, and they don't have language. It was really the politics around indirect reciprocity that was the selection pressure for the evolution of human language.
Now, I
Here
think
you
there's
talk to each other, who does what to whom, and you use names, and you try to make yourself better and make the other person worse. So this politics is coming.
now, I think you also were talking about the evolution of genomes and how the genome length is related in some way to this theory of language. I mean, there are similarities, underlying similarities. How I
Yes,
mean, I
there's
know like the genome is a code. It is a form of information encoding. But how can you? What are the commonalities here in terms of?
there is a very important result by Manfred Eigen and Peter Schuster that is called the error threshold of genetic replication, 1978 approximately, where you can give a very simple argument that evolution does not work, so natural selection does not actually find adaptation in sequence space unless the mutation rate is less than 1 over the genome length. So if you make too many mistakes, then you cannot really achieve something. And a similar phenomenon we had sort of in the language acquisition device. If the child learner ends up with a language that is very different from the input that the child learner gets, then there's too much diversity. So we called this a coherence threshold, actually, of language acquisition. And that was similar. So you needed to learn accurately enough to be understood by your peers. And how do you do this? You have to have a search space that is precise, that is limited. And the theory for that search space is what Chomsky called universal grammar.
Mm-hmm.
So universal grammar in linguistics is kind of a controversial idea, but in the way how we use it, it is a mathematical theorem. So universal grammar for us is just a statement that there must be a restricted search space for a learner who learns by inductive inference.
Mm-hmm.
And there are mathematical theorems that actually prove that.
Now, you also talk about this thing called evolutionary set theory, and I was wondering if you could articulate a bit about that, because
It was a small.
I mean, humans are different from other animals in that their social lives are so much more complex, right? In terms of the associations and that they can be a part of, the networks that they can join. How does that facilitate cooperation? The fact that we have the capacity to, choose different groups and and interact with different people.
Yeah, very good, very good. There was one paper that we wrote, and I wish to go back actually to that question because it is fascinating. So in normal game theory, you imitate the strategy of somebody. But in evolutionary set theory, you imitate the strategy of somebody, but also the community, the collection of people that this person interacts with. So, for example, I know you go to this particular country club, and you are so happy. So maybe I joined it also. Or you, as a student, you attend this class. I also go there. So this is the idea of evolutionary set theory, that we not only learn from each other's strategies, but we also join the groups of successful people. And that was one approach toward a dynamically evolutionary graph theory, because if you think about it in that context, the interaction graph, the social interaction graph is changing as a consequence of that, as a consequence of the underlying game. And this is what makes it so funny, so fascinating.
Right. So in other words, is there sort of a rule that you need to have a certain amount of mobility in order to optimize cooperation? If there's too little mobility or too much mobility, then you get suboptimal cooperation.
Yeah, I think that's completely correct. So if I can't move at all between those sets, then the mechanism is not operative. But if everybody can move immediately, then somehow the defectors can always follow the cooperators. And as soon as you have a community that works well, it is invaded by defectors. So there has to be some intermediate mobility between these sets, as far as I can remember from that paper, yes.
Now, all the things that we've been describing so far, I mean, this is in the world of descriptive. But I think, you're also thinking prescriptively to some degree, right? I mean, you believe that cooperation is good. Right? I think most of us do. But as a scientist, you're not supposed to talk about what's good or bad. You just describe things and explain things and so on. But it seems like there are a lot of practical things that you can take from this research. If you are designing a society, if you're designing an organization, if you're designing a club, right? How could we kind of use some of these insights in ways? I mean, obviously, a lot of it is intuitive. I think a lot of us who are in organizational behavior say, "Oh, yeah, this kind of makes sense." But presumably, the more we know about something, the better we can apply it. So, what sorts of things could we, as say, social engineers or organizational engineers, take from these insights?
I think the first lesson, in some sense, is already to realize that Darwinian evolution is not only natural selection. It's not only competition. It's not only fighting. Instead, the picture is a very different one. So the picture is that the biology that is in the world around us is unthinkable without cooperation. So this is what I mean when I say it is the third fundamental principle of evolution. So in my understanding, in my analysis, in my work, there would be no origin of life with cooperation. So even prior to the origin of life, there is something like cooperation between molecules. There would be no cells. So each individual cell requires cooperation of the components. There's no multicellular organism. There's no animal society. There would be no plants. And then there is no human society. There would be no human language. So without cooperation, it wouldn't work. So it's not, the world around us is not just fighting. This is the first and very important lesson, because I think in history we had terrible examples from people who thought, oh, we learn from Darwin, it is just everybody against everybody else, and only the strongest will survive. So we get a very, very different picture now from that one here. And now, if that should change the worldview, so that will hopefully change the worldview. And then we can now take individual lessons. How do we best navigate these games of cooperation? We also have to talk about this global cooperation with the future generations soon. But before we go there, even if I'm in a standard situation of direct reciprocity, what I'm seeing is that people are usually too competitive. So they usually make the strategic mistake that they think, hey, I'm now in the interaction with that person, it's either him or me. I have to win in order to move to the next round. They think basically everything is like a Wimbledon tournament or the US Open. It's either him or me. One of us will lose, one of us will win. That's wrong. That's wrong, because the winning strategies of direct reciprocity never win an individual game. So a generous tit for tat never gets more than the other person gets from that particular interaction. But it has many, many good interactions. And so therefore, humans usually destroy their own perspectives, their own payoff by being too competitive. So less competitive, don't try to win. In indirect reciprocity, we distinguish here between so-called rival strategies and partner strategies. So a rival strategy says, I will always try to get more than you. And the partner strategy says, I will accept situations where you get more than I. The only thing that I will make sure is if you really get more than I, you will get less than what you would have received had we both completely cooperated. That's a partner. So partners allow cooperation, rivals destroy everything. I think this is a very important lesson for our society, our politics. If it is all about rival strategies, everything will be destroyed.
Now, I want to turn to your more recent book called Beyond. I think you said at some point in the earlier book, you were mentioning Spinoza, and you said that Spinoza saw math as essentially a quest for the divine. And I mean, I wonder if biology for you is a form of a quest for the divine. I mean, there's a tradition, there's a religious tradition which pits nature against the divine, and then there's another religious tradition that sees them as being one and the same. Do you see religion? I mean, you're a deeply religious person. Do you see religion as part of nature?
Yes, I see religion as a human universal. So you could think of the human species that is as soon as they were able to speak, as soon as they were able to argue, they developed religion. There's no society really that didn't have religion. I think E.O. Wilson writes in the book once that even though the Soviet Union tried everything to destroy sort of the Russian Orthodox Church, the Communist Party had never more members than the illegal Orthodox Church in Russia at that time. So it is a human universal, and I think it is a search for truth. And it is the same with mathematics. Mathematics is a search for truth. So I think that religion has a very important role to play in human society. It is a healing role. It is sort of to orient us. And we suffer actually in our modern society from not really using it properly. So there's a lot of secularism out there. There's a lot of violent atheism out there. But of course, then there are also religious fanatics out there who misuse religion. So I don't in any way defend any of that. But so normally I'm oriented at sort of the scientific mind, the scientific worldview, the people around me. And a common perspective of the world would be the material world is everything there is. And the only thing that really is interesting is science. So the philosophy would be unless science studies that, it's not interesting because science explains everything. And here I would already give pause by arguing, if you say that science explains everything, what about mathematics? So mathematics is not explained by science. It is a mathematical theorem, for example, once proven, doesn't need an empiricist to make an experiment to see whether it's really true. The truth value is asserted. It's the other way around. Really good science doesn't go without mathematics. So mathematics needs science, but science needs mathematics, but not the other way around. The truth of mathematics is independent of science. So it is not true that science explains everything. And now you should pause and ask yourself, so there is something which is independent of science, which is deep truth, which is absolute truth, which is unchanging truth. Where does that live? Where is that actually, if it is not in the atoms, if it's not in the material world? So this leads us to mathematical Platonism. So for me, mathematics is a step toward a spirituality. It's a step toward the divine, as you say. And so, does mathematics lead us to God? Yes, the answer is yes, in my opinion, because it leads to a Platonic heaven, and that is already a step toward God. Does biology lead us to God? Yes, also, because biology, the best understanding of evolution is mathematical. And so, again, you need mathematics in order to understand evolution.
Now, this would be interesting. If we go to divinity schools, maybe they should start off with right, with math classes, right, in the divinity
I
schools.
think it would be, it is no, it is, I think it's well understood in philosophy that if you want to embrace what is called naturalism, so naturalism would be a kind of philosophy that would say, I'm really interested only in that what science studies. You do have a problem. How do you explain mathematics? I mean, you get pressure on this worldview by you having to deal with mathematics.
Mm-hmm.
I think
Now,
philosophers actually invent this.
this book, it's hard to describe this book because it's not a novel. It's not a poem. It's not a treatise. It's not a memoir. It's not a dialogue. It's kind of a little bit of all of those things. And of course, your work on cooperation makes its way into the book as well. But there's numerous references to um, artists, musicians, and literary figures. Do you think that scientists also fail to appreciate the arts and the role of the arts and how they help us to understand what it means to be human?
No, I wouldn't necessarily say fail to appreciate, but I think there's room, there's opportunity. So there's opportunity to write books that are sort of different, that try to explore different domains, different genres. So, for example, I have always wanted to write a book that discusses science and religion and philosophy, and I could do this in this normal way where you just write down these opinions. So this is the typical non-fiction sort of trade book. And I have a book actually almost ready also in this normal kind of formulation. But at some stage in 2019, actually early on in March 2019, I suddenly had the idea I want to discuss those ideas in the context of people talking about them. And this then came to me as a way to explain these ideas and really live through these ideas that I found actually fascinating. And I very much hope that the book will move certain people because it's supposed to be a very moving book. It's very much about love. I would call it a Socratic love story, a Platonic dialogue. But this is also love for the divine, and this is together with mathematics, it is actually love that brings us to God, and that's what I really want to communicate in that book.
Mm-hmm.
So a worldview that sort of combines science, love as ways for the divine.
Well, it sounds like also a lot of the discoveries that you made happened to you while you were walking in nature or hiking or out in the forests and so forth. I mean, is that a coincidence? I mean, is that something that you would recommend to scientists to kind of get out of the lab as a way of maybe fostering greater imagination?
No, I think I don't know how other people experience it, but for me, it is that I need to take a step back from the desk. So on the desk, I can work for many, many hours on particular problems, but sometimes you don't see the forest for the trees because these details are so in front of you that when you step up from your desk, when you get up from your desk and you start to walk outside, you take a step back and now your mind suddenly is not constrained in these particular things and you might see something bigger. And many of those big ideas then might turn out to be not so great once you come back to your desk, and then they don't actually work out, but some of them do. And I think this is how scientific discovery works.
Mm-hmm. And lastly, I mean, is if religion is such a powerful mechanism for cooperation, do we need sort of a science of religion? I mean, should we be thinking about religion not just as what you're describing, a mathematical, sort of truth, but rather as a principle for enhancing social cooperation? Is there a role for us to start studying that that relationship
Yes,
between?
I would say absolutely, absolutely. What saves mankind, in my opinion, what would increase our life expectation as a species, because right now we are doing everything to make it shorter and shorter because we are undermining the ecosystem. So we need to find ways for global cooperation and cooperation with future generations. And this is very hard. And for me, without an orientation to the divine, sort of without a recognition of absolute goodness, we will never get there. So for me, that is really the requirement. So this is where secularism actually lets us down.
Mhm. Well, I think a lot of
I
people
think
would say that in order to foster cooperation, you need to have another, right? Is it possible for us to think of ourselves, all of us, as part of humanity, as being part of one large group without having
yes,
another, without having an
so
enemy?
in my book Beyond tries exactly to do that, And here I'm borrowing very much from Hinduism. So in Hinduism, it is obviously the case that the same self resides in every person. And so this idea that when I look at you, I look at another self, but it's the same self, and the self in us is nameless, and this is the Atman, and the Atman is the Brahman. So this is already expressed in the Vedas. I find that very beautiful. And a lot of my book is also about the Bhagavad Gita, which Gandhi, of course, called the gospel of selflessness. So I think this is extremely important. So once you start to love the divine, you treat people differently. It becomes embracing. And so you also start to learn the difference between the ego and the self. There's like this shell, and we are like enslaved by the shell, and this shell has kind of a name, and that name, we want to make that name famous. And then we are sad if other people are against us also. But inside us, there is the self, and the self is nameless, and the self is untouchable. The self can only be touched by us, but not by others. This now combines Socrates and Plato together with Hinduism and with Christianity, all are on the same page here, and I find that so beautiful. So once you go to this worldview, you experience the world very differently, and there's this tremendous source of joy that suddenly overcomes you, and this is what I really try to describe in the book Beyond. So beyond this veil of confusion that is caused by this selfishness, the world looks very different. And the world looks in a way as I try to describe it in that book.
Well, Martin, thanks so much. This new book is called Beyond. It's really a remarkable, fascinating book. And of course, Super Cooperators and Evolutionary Dynamics. I think these are going to stay in print for a long time because they're really fantastic. So thanks so much.
Thank you so much. Thank you.
Unsiloed podcast is produced by University FM, elevating the stories of your institution.